So in the last segment, we derived the equipartition theorem. In this one, we're going to derive the classical formula for the blackbody radiation. So we can approximate our blackbody as a cubic enclosure whose sides are given by, dimensions are given by L. And what we want to do is that we want to compute or enumerate first the number of standing waves that we can have in such an enclosure. So to do that, we consider the wave vector, the k, and the wave vector has components. So the wave vector k is defined as, when you have a wave, and and you can use e to the power I k dot x. So this coefficient, this is the wave vector. And the wave vector is related to the wavelength, is that the modulus of the wave vector, which we can write just as k, will be given by 2 pi over lambda, where lambda is what we usually call a wavelength. So for standing wave boundary conditions, we must have a whole number of half wavelengths. And so what we will have is that if you multiply kx of L, this thing, that should be equal to, 2 pi times some integer, which we denote by x. And similarly, for ky of L should be 2 pi n of y, and kz of L should be 2 pi n of z. So what are n's? Nx, ny, nz is a 3-tuple, and it should be an element of z cubed, where each z is an integer. So by z cubed I mean z cross z cross z. So now let's consider the n space. So this is the space where the x-axis is nx, the y-axis is ny, and z-axis is nz. And in this, in this space, there will be one of these integers per unit volume. So, we could have taken a unit volume here, and there would be 1 point per unit volume. Now, if n is large enough, then we can treat n to be a continuous variable. So for n large, we can treat n to be continuous. And that's because the interval between the different integers is much smaller than n. So let's take n to be large. So we, and then what we do is that we ask the question, like, suppose we take a sphere in this space. So I'm just drawing one of the quadrants, and this is n. Suppose we take the n sphere whose radius is n, and we take a thin shell whose thickness is dn, then I want to evaluate what is the number of points that's contained in that thin shell of radius n. So of course, because geometry tells us that the volume is of that thin shell is going to be 4 pi n squared d of n. Now, what we want to do is that we want to translate it into the number of modes, because as you saw that, what we're interested in are really these k's. And so to do this, we use the relationship between k and n, and then what we have is, let me remind you, the relationship is 2 pi of n is going to be k of L, where now n, both n and k are the modulus of the respective vectors. So now if I take the derivative of this, I get d of n is going to be L divided by 2 pi d of k. So then what we do is that we take this and we transform this into into a formula that contains k. So this is going to be equal to 4 pi, then there's going to be k squared, and this k squared comes from this n squared, and there will be a dk here, but then there will be a 2 pi cubed coming from the 3 factors of k, and there will be a factor of L cubed as well. So, however, the number of modes, so the number of modes between k and k plus dk will be, it'll be 4 pi k squared L cubed by 2 pi cubed dk times 2. What did this 2? This 2 comes from the fact that there are 2 polarization degrees of freedom for electromagnetic waves. That's why we need to multiply this by a 2. So now we have enumerated the number of modes. Now what we want to do is to figure out how much radiant energy is contained in this amount of modes. To do this, we have one more step, and the step is we want to transform this formula in terms of k to frequency. So what is the relationship between frequency and k? Well, the speed of light, c, is related to the angular frequency and the wave number in this way, and omega over k. And, we could have written this as nu lambda if you wanted to. So, but what we want is, we want to express nu in terms of k, and that's given by k of c by 2 pi. And therefore, we have c is a constant, so its variation is 0. So this is the relationship we want to use. And so our final formula is going to be, if we define u of nu to be, the energy, like density, so it's energy per unit volume, the energy density, at frequency nu, then what we want to know is that what is the energy contained in the interval d nu around the frequency nu. So we want to know what is the energy between nu and nu plus d nu. Okay, and that's going to be given by this thing. So this is an energy density, so we have to divide by the volume, so there'll be 1 over L cubed. And then we have to multiply by the number of modes, and we've derived this over here. The number of mode is going to be 2 times 4 pi. And then we should have in the denominator we have 2 pi cubed, and we have an L cubed in the numerator, and then we have K. So we have to turn the K into nu, and if you do that, then we get we had a K squared here, so that'll give us a nu squared, and then we'll get a C squared, and then we'll have 2 pi squared. But there's also dk here. So because of the dk, we're going to have another factor of 2 pi and another factor of c. So we're going to have a d nu here. And for each of these modes, we are going to get a factor of kbt. This comes from the equipartition theorem. So now we just simplify this, and if you want to simplify this, what we get is this guy will cancel this guy will cancel this guy, and I think that's about it. And then we have 8 pi divided by c cubed, and then we have nu squared, and then kbt d of nu. So this is the formula for the spectrum of the blackbody radiation. So this is the famous Rayleigh Jeans formula. So now we can ask is that what is the total radiant energy predicted by this formula? So the total radiant energy, we have to integrate from 0 to infinity. So 0 u nu d nu, and so we just get our constants out, 8 pi kbt over c cubed, and inside we have the integral from 0 to infinity of nu squared d of nu. Of course, if you now do this integral, we get c cubed, and here we get 1/3 nu cubed infinity to 0, which gives us a divergent quantity. This is equal to infinity. So we see that the Rayleigh-Jeans formula predicts that the total amount of energy density from the blackbody radiation should be infinite. So note that the divergence in this formula comes from the upper end of the spectrum. It comes from the ultraviolet end of the spectrum. Because of this, this phenomena, this result is known as the ultraviolet catastrophe. So in our next lecture, we are going to talk about how Planck came up with an idea to avoid this catastrophe.